Okay, we're graphing equations by doing the transformations of the parent function. So what we're doing is creating a table with the parent function points. And then we're looking at how each of those points in the parent function table will be transferred or transformed into another position to create the new graph. Before we take off again, I want to go back with some page numbers. We talked about the fact that y is equal to x is the parent function of a line, and I just wanted to let you know what page that's on. That's on page 95 if you need to reference that, and it continues on through there. Y equal x squared is the parent function of a quadratic, and it looks something like that. It's a parabola, and you'll find that on page 194, and it continues on past there. Y equal 2 raised to the x is the parent function of an exponential growth graph. And you'll find that on page 187. Y is equal to the square root of x is a square root graph, and it looks like that. And you'll find it on page 255. And then y is equal to the absolute value is the parent function of an absolute value graph, which looks like a V, and you'll find it on page 265. So there's your basic parent functions. We have a line, page 95, a quadratic or a parabola, page 194, exponential growth, page 187, square root graph, page 255, absolute value graph, page 265. Now, if you go on into chapter 10 in my Algebra 1 book, it will show you the graphs and how to graph and transform circles and ellipses and hyperbolas, which is not really an Algebra 1 topic, but it's something that you may have done a little bit in Algebra 2, and it's something that you'll deal with in college algebra later. So that's something that you can look at on your own in chapter 10. So that's where these parent functions began. So if you notice on this one, the basic situation we see is y equal 2 to the x, which is the parent function of an exponential growth graph. Now, if we were to put it in parentheses form, we would have y equal 3 open parenthesis minus 2. And see, my basic thing, 2 to the x, is what would be inside there if you wanted to expand it. And so in reality, what we have is 1 times that plus 0. And when you have that, we could really say that there's really nothing that's happening to the x, you see. So my x's are just going to stay the same. And there's no need to do minus 0 divide 1 because it's going to be like it was, you see. And so my new x's are the same as my old x's because there was no transformation that was happening to x because there was no parentheses with anything inside of it besides subtracting 0 and dividing by 1. So my new x's are negative 2, negative 1, 0, 1, and 2. Now, we may have forgotten a rule or some rules about exponents, and this is going to be a nice friendly reminder of exponential rules as we build this table. And just so you know, on page 13 of my Algebra 1 book is where we first learned exponential rules like we're fixing to deal with, okay? So when I quote stuff, that's what I'm going to be quoting. So the parent function of an exponential graph was 2 to the x, and so we're going to put that 2 to the x in the middle, and we're going to plug in the old faithful x's of negative 2, negative 1, 0, 1, and 2. So we're going to have 2 raised to the negative 2, 2 raised to the negative 1, 2 raised to the 0, 2 raised to the first, and 2 raised to the second, which means we have to know our basic exponential rules from page 13. Now, on page 13, there's an oval in the middle of page 13, and it says the negative on the exponent, reciprocates it. It's a command to take the reciprocal. Here's how you read this. You read this as the reciprocal of 2 squared. Now what's 2 squared? 4. What is the reciprocal of 4? 1/4. Everybody understand that? The negative is a command to reciprocate. We read this negative on that exponent as the reciprocal of. So we say the reciprocal of 2 to the first. Well, what's 2 to the first? 2. And what's the reciprocal of 2? 1/2, so we get 1/2. And then another one that people tend to mess up on, if you haven't done your memory work, any number raised to the 0 power is 1. Any number raised to the first power gives you that number, or itself. And to the second means times itself, which would be a 4. So my old y's are 1/4, 1/2, 1, 2, and 4. That's my old y's. Now there is some stuff that's happening to y. And what's happening to y is what's outside the parenthesis, and it happens according to the order of operations doing, right? So we've got multiplication and subtraction. Which one would you do first? Would you multiply or subtract first? You would do, we're doing the order of operations. You do multiplication before you do subtraction. So what we're going to do to y is times 3 minus 2. Now this gets a little more fun with fractions, but we're good at those, and our brain's just full of good math stuff, so we'll try to do it in our head. If not, you can punch it in the calculator. What's 3 times a fourth? 3/4. 3/4. 3 times a banana is 3 bananas. 3 times a fourth is 3/4 minus 2. Now 2 is 8/4, correct? Hopefully we can do that in our head quick. So we have 3/4 minus 8/4 is negative 5/4. Buddy can do that, right? 3 times a fourth is 3/4. 2 is 8/4. 3/4 minus 8/4 is negative 5/4. Okay, now we've got 3 times a half. 3 times a half is 3 halves, just like 3 bananas. Again, minus 2, which is 4 halves, right? Minus 2, which is 4 halves. So we have 3 halves minus 4 halves is negative 1/2. And then we have 1 times 3 is 3, minus 2 is 1. And then we have 2 times 3 is 6, minus 2 is 4. And then we have 4 times 3 is 12, minus 2 is 10. And so there's my new y's. And again, what we're going to do is we're going to graph the original parent function. Those 5 points changed into these 5 points, right? So we're going to graph the old one and the new one, but we're going to do it 1 point at a time to watch how each point moved and transformed into the new equation, okay? Now, from what we learned a long time ago, what would we say about this? What would the minus 2 cause to happen to the original graph? Shift down 2 and then get steeper, right? Shift down 2, get steeper. That's what's going to happen. It's going to shift down 2 and get steeper. Well, we're going to watch that happen, and y'all can remind me of the numbers if I forget the numbers, and we'll graph these together. Okay, so the first parent function point was negative 2, 1/4. Negative 2 and up 1/4. We're going to have to guess the measure, maybe somewhere in there. And the new point was at negative 5/4. It was at negative 2 and 5/4, right? So negative 2 and then negative 5/4. Well, negative 5/4 is equal to negative 1 and 1/4. So it's going to be at negative 2, but then we're going to have to go down negative 1 and 1/4, so it ended up there, correct? We changed that negative 5/4 to negative 1 and 1/4. And then the second point went from negative 1 1 half, negative 1, negative 1, 1 half, it ended up at negative 3 halves. So it ended up at negative 1, negative 3 halves. And we know that negative 3 halves is equal to negative 1 and 1 half as a mixed numeral. So we're going to go to negative 1 and then negative 1 and a half, which is, oh, it was just 1 half. That's better because that was fixing to go the wrong way. That was negative 1 half. So it was negative 1 and then negative 1 half, which is here, which I need to do in red. So that second point shifted to there. The third parent function point was at 0, 1. It shifted to 0 and what? And what? 1 stayed in the same place. Okay. The fourth point was at 1, 2. It shifted to 1, 4. The next point was at 2, 4. And it shifted to 10. 4, 5, 6, 7, 8, 9, 10. So the original graph, now you realize that it's approaching that x-axis. Do you see that? There's an arrow there. It infinitely approaches the x-axis but never touches it. We call the x-axis a what? You remember that word for it almost hits it but it never does? Is it one S or two? Asymptote. The asymptote. Remember that? Okay. So it's going to approach that x-axis and never hit it. And then it's going to infinitely rise. Okay? So there's your parent function of an exponential graph. And it shifted to here. Now, there would be another asymptote somewhere, okay? If we went down 2, you understand there's an asymptote here that thing's approaching. And now the asymptote is at negative 2. So it's going to approach and go up like that, okay? It's so the asymptote shifted down 2. That's at minus 2 in that equation, and then it got steeper. Yes. Yes. Yeah, I missed. Yeah. Yes. But it's going to approach that. It's going to approach that. X is negative 2, that y is negative 2, horizontal line, and never hit it. So your asymptote shifted down 2 because of the minus 2, okay? Any questions on the transformation of the parent function of an exponential graph? Okay? All right. Now we have an absolute value graph. The parent function of an absolute value graph is y equal absolute value x. Now, if we had y is equal to x, remember when we graphed, it did this. What happens if you see that y cannot be negative, right? And since y cannot be negative, all of these negative y's end up becoming positive y's. So the graph, it turns into a V, right? That wing bends back up, basically. Okay? So we're going to take what y is equal to and put it in the middle and build a table. We're starting with the old faithful x's, so absolute value negative 2, absolute value negative 1, absolute value 0, absolute value 1, absolute value 2. Absolute value represents distance. I'm quoting page 88 of the Algebra book. There's no such thing as a negative distance. Absolute value is always positive. Positive, 0, 1, 2. So my original x's were negative 2, negative 1, 0, 1, 2. My old y's are 2, 1, 0, 1, 2. And we're going to look at the effect that those new numbers are going to have on the x and y of those parent functions. We're going to graph the new equation based on the transformation of the parent function points. So what happens to x is what's on the inside in the reverse order of operations. And so I have multiplication and subtraction, and it's according to the rules of undoing. Which one would you undo first? Subtraction by, so we're going to add 1. And then we would undo multiplication by, so we would divide 1. Everybody understand what we're doing to the x and y? Now, what's happening to y is what's on the outside, and it is according to doing in the normal order of operations. Which one would you do first? Multiply. And which one would you do second? Addition. So what's happening to x is what's on the inside in the reverse order of operations according to undoing. And what's happening to y is what's on the outside in the order of operations according to doing. Okay? So we'll run through this. Negative 2 plus 1 is negative 1. Divide 1 is negative 1. Negative 1 plus 1 is 0. Divide 1 is 0. 0 plus 1 is 1. Divide 1 is 1. 1 plus 1 is 1. 2. 1 plus 1 is 2. Divide 1 is 2. 2 plus 1 is 3. Divide 1 is 3. And then the y's, 2 times negative 3 is negative 6 plus 2 is negative 4. 1 times negative 3 plus 2, negative 1. 0 times negative 3, 0 plus 2, 2. 1 times negative 3 plus 2, negative 1. 2 times negative 3, negative 6 plus 2, negative 4. So my new x's are here. Negative 1, 0, 1, 2, 3. My new y's are here. Negative 4, negative 1, 2, negative 1, negative 4. Again, we're going to take these original parent function points and graph them. They have been transformed into these new points. So we're going to graph each one and see where it ended up, and end up with a perfect graph of y equal negative 3 absolute value x minus 1 plus 2 by transforming each of the parent function points. And it's just, to me, it's cool how the order of operations makes everything happen mathematically. I just like it. It's just neat that works, okay? So let's look at the original point. So my first original point was negative 2, 2. It was transformed into negative 1, negative 4. My second point was negative 1, 1. It was transformed into 0 what? 0, negative 1. Good. My third point was 0, 0. It was transformed into, what's that? 1, 2. Cool. The next point was 1, 1. It was transformed into 2, negative 1. The next point was 2, 2, and it was transformed into, what's that? 3, negative 4. I can look and figure that out, couldn't I? So my original graph is this, and my transformed graph. Whoa, shoot, whoa, sheriff, he's right. Okay, is this. Now let's talk about that. My equation was y equal negative 3 absolute value x minus 1 plus 2. Let's go back and remind ourselves of what we said would happen if we did each of these things, okay? What did we learn in Algebra 2 would happen if we had 2? Shift up 2. What did we learn would happen if we had a minus 1? The opposite of minus 1, which is plus 1, so it would do that, right? And what did we say would happen because of the 3? Wings get steeper. I over-exaggerated that, sorry. And the negative makes it go down instead of up, and we ended up with the blue, okay? So you had talked about in Algebra 2 what each of those things will do. And all you could have done with that is get in approximately the right direction. You would have known from that it shifted up to right 1, got skinnier, and goes down, but you would not have known how much skinnier. You wouldn't have known the width of this, see. But with parent function transformations, you can deal with all of that stuff and get in the exact right spot instead of it's about right here, see. Any questions on what we've done? So we've done a little bit better job than just, okay, it's about here. Although we still need to know that it's about here stuff, okay? Okay. Now we have a square root graph. The basic square root graph was y equal square root x. Now, notice I changed the numbers. And I did that on purpose because we don't want to get a square root of 3, which is some non-repeating, non-terminating decimal, a radical, irrational number. So I started with negative 1. Why do you think I would do that? What's the square root of negative 1? It's I. It's an imaginary number. The graph just kind of dies out. You can't take the square root of a negative. So any negative you plug in, there's not an answer, because the coordinate plane represents the set of all real numbers, correct? And then we would have the square root of 0, which is 0, and the square root of 1, which is 1, and the square root of 4, which is 2, and the square root of 9, which is 3. Notice the old faithful negative 2, negative 1, 0, 1, 2 wouldn't work very pretty. So when we're dealing with square root, we want to choose perfect square x's, right? X is our independent variable, it's our input, and we're going to input something that's going to give us some decent outputs, okay? And so my old y's were I, 0, 1, 2, 3. Now, somebody tell me what this really looks like. This is y equal 3, open parenthesis, minus 1. I want to know what goes right there. This is back to page 13. Rules. We learned that the negative on the exponent means reciprocal. Anything to the 0 power is 1. Anything to the first power is that number. Square means times itself. And what means square root? The 1/2 power. Remember, square root's the same as the 1/2 power. So this really looks like this, you see. There is a grouping symbol understood, and the exponent that's understood on that parentheses is a 1/2 power. So we need to kind of start remembering those fractional exponents. Now remember that what's happening to x is what's on the inside, 1 times x, 1 times x plus 2. And what's going to happen to x is we're going to undo, correct? Which one would you undo first? addition by subtraction, and then you would undo multiplication by division, and we know if you divide by 1, it's the same thing. Okay? And what's happening to y is what's on the outside. And we do it according to doing. And which one do you do first? Multiplication. So we would multiply by 3 and then subtract 1. So what's happening to the x is what's on the inside according to the undoing properties. So you use inverse properties and you inverse the order of operations. What's happening to y is on the outside, and it happens according to doing, according to the normal order of operations. Okay? So negative 1 minus 2 is negative 3 divided by 1 is negative 3. 0 minus 2 is negative 1 divided by 1 is negative 2. 1 minus 2 is negative 1 divided 1 is negative 1. 4 minus 2 is 2 divide 1 is 2. 9 minus 2 is 7 divide 1 is 7. So there's my new x's, negative 3, negative 2, negative 1, 2, 7. My y's, I times 3 minus 1 is 3i minus 1, which is a complex number. We would write it as 1 minus 3i correctly. That puts it in the form of a plus bi. Remember that? But you can't graph it because it's still imaginary. And then we have 0 times 3 is 0 minus 1 is negative 1. And then we have 1 times 3 is 3 minus 1 is 2. And 2 times 3 is 6 minus 1 is 5. And 3 times 3 is 9 minus 1 is 8. And so we have 1 minus 3i. We have negative 1. We have positive 2, positive 5, and 8. And I'll let you catch up. You just have to do the work. Do the math. Everybody catching up? I'll give you a few more seconds. And then we're going to graph these. Remember that the parent function of a square root looks something like that, right? Why did it die? How come it doesn't just keep going? Because of those imaginary numbers. You can't graph those, so it just kind of fizzles out. Okay? There's not an asymptote, it just stops. Or it just hadn't started yet, whichever way you want to look at it. Okay? All right, so let's graph those. So our first thing was negative 1 and I, which we couldn't graph it. So you can't put a dot because there's not an I for y. So the next one was 0, 0, right? So my graph starts here. And the next one was, oh, I'm sorry, that turned into what? Negative 2, negative 1. It ended up way over here. The next one is 1, 1, and it turned into, what's that? Negative 1, 2. The next one was 4, 2. And it turned into 2, 5. The next one was, and it turned into, what's that? 7, 8. Now my equation was y equal, was it 3 square root of x plus 2 and then minus 1. So what did we say was going to happen because of the minus 1? it would have shifted down 1, right? What would happen because of the plus 2? The opposite of a plus 2, which is a minus 2, right? Shift left 2. What would happen because of the 3? Steeper. Okay? So you can see it's actually doing what you learned in Algebra 2, but we would have said it shifted down 1, left 2, and got steeper, and we would not have known exactly how much steeper, but now we can say exactly where it's at. Okay? Any questions on that? So we've transformed a linear, a quadratic, an exponential, an absolute value, and a square root. The next thing we want to do is look at how to graph a quadratic normally, not going through all this parent function transformation stuff, but how do you build a pretty table and a graph of a regular quadratic, okay? Now, it's going to tell you how to do this exactly on page 195A of the Algebra 1 book. And I suggest that you go there and look at it because it's in words. It says step 1, do this. Step 2, do this. Step 3, do this. Step 4, do this. It leads you through the steps, exactly how to do this. And if you don't study that, you may not do so well. What we're not going to let you do is just throw it in the calculator and hit enter and look at your table. Okay? We're not going to let you go to y equal and pull it up on the calculator. You have to do this on paper to show the calculations so that we get a nice, pretty little parabola. Okay. The first thing we need to know is that the standard form of a quadratic is y equal ax squared plus bx plus c. We got to know that. So we've got to know that the a is 2, and the b is negative 12, and the c is 22. And then it's going to tell us exactly where to go from there to get our line of symmetry, to get our vertex, and to build our table. It's going to take more time than I have left. So we're going to stop right there. You can, even if you're going to watch the next video, I would suggest before you watch the next video to go to page 195A and read it, and then watch the next video. Anyway, we'll stop there for